In this video, we are going to discuss about two very important topic for your upcoming examination, that is the speed control of DC machine and the 3-point starter. And before we start or we go to the speed control of DC machine, we have to uh, derive a expression, that is the EMF equation of DC machine. So let's go with the EMF equation. So let's put the heading EMF equation of DC machine. So before we start, we should know some important point that you must know. Uh, Let P is equal to the number of poles of DC generator. I'm not going to mention the DC because this chapter is entirely upon the DC. So, and the second is the phi is the flux produced by each pole. Flux produced by each pole. That means the number of pole is P and the flux produced by each pole is phi. So the total flux produced is phi into P. We'll go there later. Now in it's very important thing because this is the topic we should stick over here, that is the speed, and we have to control the speed by various method, but the here n is the speed of armature of generator, and it is obviously in RPM, rotation or revolution per minute. Okay, now next important thing is Z. It is very important. There is a total number of conductors in armature. Total number of conductor in armature, important thing. And the A, it is the another important thing you should keep on your mind, that is the number of parallel path in which armature conductor are distributed. Armature conductor are distributed. Okay, now go to the derivation part. Okay, so obviously you should start with the Faraday's laws of electromagnetic induction. So first we should write from, let's change the color, Faraday's laws of electromagnetic induction, EMI. You should write it properly. So if I write it from in the descriptive manner, then the video length should be high. So from Faraday's laws of electromagnetic induction, we know that E is equal to d phi by dt. This is the, if Faraday's law, and the minus, you the one question may arise in your mind that why I am not writing the minus over here. Here because of that minus is given by the Lage, and that minus denote the action and the reaction both are in the opposite side. So now the story starts. The story is, so if it has a p number of poles, I've already told you, then during one revolution, if there is a p number of poles, that is the number of pole in the total machine, that is a DC generator is p, and for one revolution of of armature, each armature conductor cuts magnetic flux p time, because number of pole is p. So we can write, if it has p number of poles, then during one revolution, you should write this in your examination properly, of armature, each armature conductor cuts magnetic flux p times. So the flux cut by one conductor in one revolution is p into phi. So the flux cut by one conductor in one revolution is equal to p into phi Weber. Okay, important. Since the number of revolution made by armature per minute is n, because it is in rpm, the rotation per minute. So since n is in rpm, this m is most important, rpm. So number of revolution per second is, what is the number of revolution per second, is n by 60, because in 1 minute it is a 60 second to 1 by 60, and therefore and therefore, the important thing is, you can change the color of the pen. Flux cut by each conductor per second is equal to what? That is the phi into p into n by 60 is equal to, we can write it, flux cut by one conductor per revolution. It is already, we can derive, that is a p into phi into number of revolution of armature per second. Okay, that means this is nothing but the phi into p, that is the flux cut by one conductor per revolution. This is already phi into p is here, and is number of revolution of armature in 1 second, that is the n by 60, that is the n by 60. That means phi p n by 60 r, sorry, not rp, it is with Weber, there is the flux Weber. Okay, now, so the induced EMF, so the flux cut by each conductor per second, that means that is the change in flux per second is nothing but the phi pn by 60, and flux, there is a change in, or the rate of change of flux or rate of change of cut of flux per second is nothing but the induced EMF. So what is the induced EMF? Go to the next page. So the induced EMF, so we can say So the induced EMF E is equal to nothing but the phi P into N by 60, because that is the rate of change of cutoff flux per second. Okay. Now important thing, that is the now Z comes into the picture. If Z is the total number of conductor, then the induced EMF. So the this is the induced EMF for one conductor. Okay, this is for one conductor. So the EMF induced for Z conductor is what? That is the nothing but the E total, or you can say that capital E, you can say it is a capital E, is equal to what? Z into phi Pn whole divided by 60, because there are Z conductor now, but Z is what? Z is the total number of conductor in an armature. Now, how the Z is situated, and the A is the number of parallel path in which the armature conductor are distributed. That means here the the conductors are like this: one, second, third, like this. There are so many parallel conductors are present over here, and we are going to give you this is the E, induced EMF E. So whatever the induced EMF over here is same is over here, is same is over here. So the number of conductor in the armature is now Z, and the number of parallel path is A. Now, so that is, you can write the important thing that here, from here the exact final EMF equation comes, but these Z number of conductors have a number of parallel path. So the EMF induced effectively is the EMF induced in each path. Whatever the total induced EMF in this path is phi Z Pn by 60. Here it is 60. The type error 60. Okay. Now the total induced EMF over here, this Z number of conductor is phi Z Pn by 60, but that Z number of conductor is divided into a number of parallel paths. So the effective induced EMF per path is E is equal to Z phi Pn by 60A. This is your EMF equation for your EMF equation for DC generator. Okay. So now you can think one thing, that is the P. P is what? P is the number of pole. It is a constant, because it is up to you. That is depending upon the what kind of generator you are using, that how much pole have that generator is. Okay. And that Z by A, Z is what? Z is number of conductor, and A is the number of parallel path in the conductor. That means how many parallel paths are there. That is also it in our hand, and Z is the number of conductor, that is also in our hand, and so Z by A is also a constant. So here two constant we are getting, that is the, so now we can say that E proportional to phi into N. This phi into N, 60 is constant, Z by A is constant, P is constant. So E proportional to phi N, or you can say E is equal to Kn, K phi N. Okay. Okay. Now come to the important thing, that is the speed control, the for which I am making this video, that is the speed control of the DC motor. Now give the heading speed control of DC motor. How we can control the speed? That means, so starting from the EMF equation, that is nothing but the back EMF. That means the diagram for motor, if we draw the diagram of motor, so you can say this is your RA, that is the resistance of the armature resistance. So we can make it more large. This is your RA, that is the armature resistance, R small a. Now we can draw the diagram like this. So this is your, these two are the carbon brushes. Now taking this is your motor, and here you can say this is a shaft and this is a load. Okay, so for that we are, this is a positive terminal, this is a negative terminal, and we are giving the supply of E or V. V is your supply voltage. For V is, as V is your supply voltage, and if I A is flowing through, that is the armature current which is flowing through the current flowing through the armature, that is armature current. Now if V you are applying in this direction, then the EMF is over here induced is in this direction, that is the the direction of the E and the direction of V is the opposite side. And I have already discussed in the class that how in transformer the EMF is induced in the opposite side. E is equal to minus n d phi dt. From that relation we can relate it. Okay, so it means that if this is the diagram of the motor, then we can say that the equation for back EMF, so the equation for back EMF is what? It is nothing but the E is equal to P N Z phi by 60 into A. I have already discussed in the early earlier page. Okay, now here we are going to discuss about the control of the speed. Now what is speed? N is the speed over here, so we can write N as E60 A into E by P Z phi. Okay, now A Z phi are constant. I already told you A is the number of parallel path in the conductor in the armature, Z is the number of Z is the total number of the conductors in the armature, and phi is the flux. That flux is dependent upon you, that how much voltage we are, that is the applied voltage is how that much of if we are applying the V amount of applied voltage, then according to that IA is there, and depending upon the IA, as IA and phi both are in the proportional, so as I is developed, then the phi is developed. So phi is up to us as I is up to us as V is the supply voltage. Okay, now this is equation, you can write this is equation 1 and this is equation 2. Okay, now so that we can say that N is equal to E K by phi, because A, Z, phi all are the constant. Or we can say that N is equal to E by K into phi. We can say it as, we can K, you can take K as a constant, or you can say that K inverse as a constant. Okay, so N is equal to E by K phi. This is equation 3. This is the most important equation. Okay, so we can say the important thing, that the N here, the what is our finding? The finding is N is depend upon E and phi. Okay, E and phi. Now Now how they are related? Now let's N1 is your initial speed, so N2 be your final speed, because here is some variac and we vary the there is some variac, and we vary the apply voltage slowly, that is the from 0 to 230 or 220 volt. So initial speed at the zeros there is some speed, and at a range of 230 or 220 volt the speed is different. So there are initial and final voltage. Okay, final speed depending upon the initial and final voltage. Now secondly we can say that E1 is your E1 is your initial value of EMF, initial induced back EMF, and E2 is your final induced back EMF. Okay, this is also you can say that depending upon the N1 the speed, the back EMF is also, that is the speed means the voltage, applied voltage. If applied voltage is increases, then speed is increases, and the obviously due to the speed the induced back EMF also increases. Now if phi 1 is the initial induced flux, because flux is the important parameter, because depending upon the flux, rate of change of flux is nothing but the, it is the determination of the induced EMF. Okay, so if phi 1 is the initial induced flux and phi 2 is the final induced flux, now we can write n1, we can write n1 is equal to E1 by K into phi 1, and obviously we can say that N2, this is the equation number 4, and N2 is equal to E2 by K into phi 2, this is the initial equation number 6. Now sorry, for 5. Now equation 5 is divided by equation 4, what we get, that is the N2 by N1 is equal to nothing but the E2 by K phi 2 by E1 by K phi 1. Now what is our finding? So En2 is equal to N2 by N1 is that. That means that N2 by N1 is nothing but the, is equal to, we can say that, we can make it simplify, E2 by K phi 2 into K phi 1 by E1, that is the K is cancel out, so E2 into phi 1 is equal to E1 into phi 2. Okay, it means that N2 is, N2 by N2 is proportional with E2, and N2 is proportional with E, N is proportional with E, and A is inversely proportional with phi. Here is also the same criteria is there. Okay, now how we can control the, so it means that that is the N2 and N1 is dependent upon the E1 and E2, sorry, E1 and phi 1 or E2 and phi 2. That means the speed is dependent upon the back EMF and the phi flux. Now for this, if we are considering this equation, we can uh, we can take this diagram in the next page, at the next new page. Now for this, so if so we can write the equation, back EMF equation. So EMF equation, so what is the EMF equation? So EMF equation is what? V minus IA RA is equal to E. Okay, this is the back EMF. Again I am saying that is that RA can we can write, you can draw RA over here. So V minus potential drop IARA is equal to the induced back EMF E. So V minus IARA is equal to E, or we can say that V is equal to E plus IARA. Okay, this is the one equation. Okay, okay. So, and the another equation we get, that is the speed of DC machine is what? N is equal to E by K into phi. Now we put the E as V minus IARA, that is the V minus IARA. Instead of E, I can put V minus IARA by K into phi. Okay, so this is the, so N is equal to V minus IARA by K phi is the basic equation for the speed. Okay, so now we can say that this is the equation for speed. It means that speed, the note, main note, is the speed depends upon what? That is the applied voltage, that is the V, this V, the flux, that is the phi, and obviously the armature resistance RA. That means we can control the speed by varying the applied voltage, by varying the flux, and by varying the armature resistance. And N is proportional to RA. That means that if armature resistance is increases, then if armature voltage increases, then speed is what? Speed is, that means if this portion is increases, then the numerator is decrease. As numerator is decrease, then the speed is decrease. So N is proportional to, so it means that if RA is increased, then IARA is increased. So V minus RA IARA is decreased. If it is decreased, then this by this is obviously decreased. That means the, if previously it is the 12 by 8 and now it becomes the 10 by 8, which one is larger? This one is larger. So if this portion IARA is increased, then this part is decreased. That means the RM, that is the armature resistance, is inversely proportional with the N. And obviously from this you can say that N is inversely proportional with the 1 by phi. That is the inversely proportional with the phi. That is, if by phi is increased, then the N is decreased. How we can easily control this speed by this phi. Okay, the control of phi, and this is obviously this is in your syllabus. So if this question comes that the how the write down what how you can control the speed of the DC motor, then you should, up to this you should write. Then you can give any one method, any method for the speed control. Let's do the uh, flux control method. That is the one is the first is the armature resistance. That is the armature resistance control, armature resistance control. That means the by controlling the armature resistance, we can change the speed of the DC motor. Second is the voltage control. That is the V, and this method is called the Ward Leonard method. This is very important for the fourth semester electrical students. And third one is nothing but the field flux control, and how we can control the field flux, that by adding one extra resistance with shunt with the RSH. Okay, so this is your diagram, basic diagram for a DC motor. Now here we can, this is your, here we can connect one RA, that is the armature resistance, and this is your applied voltage V over here. Now we can connect one extra resistance, this is the resistance, one extra resistance, we can draw it with red color, this is the RE, that is the R external, with a field winding, that is the RSH, that is the shunt field, this is the RSH. Now this field has some resistance RSH. Now in the previous case, what is the value of whatever the RSH is? Now if we add one extra RE, that is the one extra resistance, then the value of the resistance is increased, and if the value of the resistance is increased, then the speed can be controlled by the by the flux control method. Okay, that means we can draw this diagram like this. So N is what? We know that N is equal to V minus IARA by K into phi. This is we know. Okay, that means nothing but the E by K phi. We have already derived it. Okay, now N, now if an external resistance is added, then with field winding RSH in series, in bracket in series, then the current for field winding is what? ISH is equal to V by RSH plus RE. Previously it was ISH was V by RSH. Now it is V by RSH plus RE. It means that, so ISH is decreases because this part is increases. So as RSH plus RE is increases, then ISH is decreases. So if ISH is decrease, then phi is also decrease because I proportion to phi. So if ISH is decrease, then phi is decrease, and if phi is decrease, if phi is decrease, then N speed is increase because N is inversely proportional with phi. Okay, so our motto is to decrease the ISH so that the phi is decreased, and if phi is decreased, then the speed is increased. So this is the entire thing about the speed control. Now the second is the 3-point starter. Okay, so first, so before we go to the 3-point starter, we should know what is the 3-point starter and what is its use, means what is the need of the 3-point starter. So this is the diagram for the 3-point starter. Before that, we are going to discuss about the what is the use of the 3-point starter. So need of, first of all, write down, and then need, the heading is 3-point starter. What are the 3-point? The 3-pointer L, this is the F, this is the A, this is the L line, this is the F field, and this is the A for armature. Okay, so LFA starter, there are also another two types of starter, one is 2-point starter and the 4-point starter, but in your syllabus we are discussing the 3-point starter. So what is the need of starter? First, need of starter. Whatever the starter is, what is the basic need of the starter? Starter means which can start the motor. It means it is a protection device. So now we can again draw a simple diagram for a DC machine. Okay, see, this is, we can give the RA over here. This is a resistance RA. This is your supply. So supply is your V, and due to that IA is flowing over here. IA is flowing over here. Okay, RA is the armature resistance, and for that this is the induced EB, back EMF. EB is generated. EB stands for back EMF. Okay, now the starter is, it is due to the back EMF produced in motor, which plays a vital role to control that the back EMF. That means that the back EMF is dangerous as it can produce the current. How? That when the motor, the that means that if we write down the equation of the EMF equation, that we can write a V minus IA RA is equal to V minus IA into RA is equal to E into B, back EMF. Now V is equal to EB plus IA RA. Now what is the problem? Acha. Initially, so so when the motor armature rotates inside the magnetic field, the back EMF induced. So when the motor armature rotate inside the magnetic field, the back EMF EB is induced. Okay, Achha. According to the Faraday's law of electromagnetic induction. So the EB opposes the supply V. Okay, now at starting, that means EB is what? EB is equal to 0, because at starting when the very small amount of voltage V is applied, then back EMF is 0. So as back EMF is 0, so what is V? V is equal to IA into RA. That means the V is small. Why it is small? Because IA RA is small, because IA is small. RA is the constant. RA is dependent upon us, that is the RA is the armature resistance, and that is in our hand. But V, we can vary V from 0 volt to 220 to 30 volt. So initially when V is very more small, it is tends to 0 or 1 volt, 2 volt, then back EMF is 0. Then IA is what? Is equal to V by RA. Now for DC machine, RA small, very small, so V by RA is much high, as it means it means that IA is very much high. So if IA is high, then this IA is dangerous for our human body. So this IA is dangerous for us. It means when the motor runs in rated speed, then EB is not equal to 0, and if EB is not equal to 0, then there must be, so EB, the V minus IAR is equal to EB, So V is equal to IA RA plus EB. Then IA is not that much small. So to overcome this, we have to introduce one device that is called a 3-point starter, and this 3-point starter is nothing but the L. This L stands for the line, F stands for the field. Here you can draw one field, and here you can draw one armature is the one armature winding. Okay, now how we can draw the armature winding. So here in with red color I am draw one field winding that is useful for you to relate this diagram. So this is your armature A1, this is your A2, and this is your F1, and this is your F2. Now we can say that, so this is what, this is your start. Okay, so that starter is a variable resistance, is nothing but a variable resistance. Here 120 1 2 3 4 5, these point are nothing but the starts. There here one copper, so copper strip is there, one copper strip is connected over here. This we can make it red color, bold red color. So here one copper strip is there, copper strip is connected. By this copper strip, this handle is rotates, this handle, this is the handle, and the handle here one small iron piece is there. This piece of iron, when it's go from here to here, then this and this are both are stuck together. Okay, so now here you can say that these two parallel line paths are there. One parallel path is this, and another parallel path is this. So one thing, so why it is called 3-point starter? Because L, F, and A 3 points are there. That's why they are called the 3-point starter. So L is connected to here. It is called the OLR. That is the overload. OLC, you can say OLC, overload circuit, or we can say that OLR, that is the overload release. Overload release, and it is the, here it is called the NVC, that is the no volt coil. No volt coil. Now what happened? So when the lower end of the conducting lever, there is a lower end, this is the conducting lever. So lower end of the conducting lever um, uh, of starter, handle was attached over here. Then okay, so you can say that this is one electromagnet, this is another electromagnet. Okay, one, this is one stands for off, or 5 stands for run. It means when this handle is in this off position, then this armature have resistance, this to enter resistance plus the armature resistance, because you can see that this resistance is connected with the armature. Now when the when these electromagnets magnetized, then and we slowly we move this handle from 1 2 3 4 5 4 5, that means the from off position to run position. At the run position, when this lever is at one position, then the resistance is this entire resistance plus the armature resistance. When this point is stuck to the fifth point, then only the resistance is this resistance. What is our motto? Our motto is to increase the resistance when at the stop position. It means when initial position, when EB is equal to 0, then it is very dangerous, as IA is very high. When EB is 0, then only V is equal to IARA, because EB is 0. So V is equal to V minus IARA is equal to 0. So V is equal to IARA. So as V is equal to IARA and as RA is very small, so IARA is equal to IA is equal to V by RA. So as RA is very small for DC motor, then IA is very much high. So this is our motto, that when the motor is in stop position, that is the off position, then we should connect some resistance over there so that Ra is less, and as Ra is less, then the motor is safe and we are safe. When this handle go from 1 2 3 4 5, that is the run position, then obviously this external resistance cut from the armature resistance, and as it is cut, the, but there is no issue, because as when the motor is in full run position, then Eb is not equal to 0. Then IaRa become, then V minus IaRa is equal to Eb max. That means that at the maximum position, so V is equal to Eb max minus IaRa, so sorry, plus IRA. So we are getting some value over there, and as we are getting some value over there, then IA is decreases. So that means the this handle, when the motor is in off position, it means that we are incorporating some variable resistances. As the speed is gradually increased, that means that as the applied voltage, because this is the supply, we can make a supply over here. This is the line, a line and field. So the supply is like this. Here it is the supply. This is your supply. Okay. Now, when we are supplying to the supply, what happened? So this is your supply. So when it is supplied, then this OLR is activated, then this coil is also activated. This is also activated. Now we are going to move this handle over here, and this soft iron piece is stuck over this M1. When we are going to give the supply, then initially the direction of the current is in this direction. Okay, now that means the entire thing is connected through the field. No current is flowing through the armature. Now when this starts over here, then the current is flowing in this direction, as well as the armature direction, as well as the armature winding also. Then the current flowing through the armature winding, but that gets this amount of internal resistance, external resistance, which we incorporate. And if as the speed of the DC motor increases, then as the if speed of the DC motor increases, then the external resistances which we incorporate out from outside, that is also decreases, because this handle go from 1 to 2. 1 to 2 means this portion is out. 2 to 3 means this portion is out. 3 to 4 means this portion is out. Like that, when it is in fifth position, this entire the external resistance is out, but there is no need of external resistance, because at that point EB is maximum, and as EB is maximum, then there is no extra current IA is flowing through the motor which can damage the motor or which can damage our human body. Okay, so this is the entire thing about the DC motor, which you got, I think you can got in your upcoming examination. So if you need, you just comment me. I will give you the entire working principle and the construction of this 3-point starter. So in the next video, I am going to discuss about the torque slip characteristics of three-phase induction motor and some other questions that is not confirmed related